In this video, we are going to give you some tips about how to actually implement the autoregressive models from this formula by using a neural network or other ways that you can model things. So let's go to the whiteboard.
Okay. So I'm assuming that you already know some framework like PyTorch or TensorFlow. So I'm more familiar with PyTorch with Lightning. I prefer that one. I used TensorFlow a lot previously and Keras, and I actually like Keras a lot. But right now I'm doing a lot of things in Lightning. So I'm assuming that you already know some frameworks. So if you already know some frameworks, how do you actually implement this kind of models? Let me write it down. Px is equal to the product from I to from 1 to n, and the p xi x1 to xi minus 1. So this looks very complicated. However, all we need to implement is simply this guy. So although it writes in a product form, what we actually need is given the history of the input, then we can predict the next one. That's all we need. Okay, so by implement neural network or any kind of model, you want to focus on what is the input and what is the output and what is the loss should be. So we separate this discuss in two cases. So first case is discrete output. It's more like so the input we did the input later, but the output is xi. So xi might be something discrete, like when you do the classification, like MNIST or CFR10, there are 10 different outputs. So this one is discrete. So the other case is the continuous output or the output with topology. So the major difference is that the discrete output has no structure for a different outcome. However, the regression one, the continuous one, has some structure, which we usually told which is often the structure is often the topology of the output. So what does it mean? So consider your correct output should be 92. This might be a score or grade of one of the tests, or maybe in other cases like a lottery number. So consider your prediction is 93. Is this one good or not so good? So if you are considering predict the test score, then 93 might be kind of good because it is definitely much better than 60 if your prediction is 60 or prediction is 100. So 93 is definitely more accurate than the 60 and the 100. In this one, we know, although we might only have some finite, even in the example of lottery numbers, we only consider one single number, or in the grade that you get from a test score, it might just have from 0 to 100, and you always get an integer score, even if the output space is discrete and finite. We know that the output might have some structure because we know that 93 is more accurate than 60 and 100. However, if we are considering a lottery number, so if we are considering a grade or score, 93 is better than 60. However, if you are considered as a lottery number, no matter your prediction is 93 or 60 or 100, they are equally wrong. Although you might feel, okay, you are just unlucky, you are just missed by one number. However, in the rules, they are just different symbols. 93 is not closer to 92 than 60 or 100 if you consider you are buying a lottery. So in this case, this output for the lottery case, these outputs are discrete. However, if you consider your score or like a test score, then that one is more like a regression or like a structure or continuous output. Even though these outputs are all finite. You can imagine a lottery. It consists just one number, and the number can be chosen from 0 to 100, and it should be integer, just like a test score. So the difference is between a discrete output or a regression output is not whether it is just integers or whether it is finite. The major difference, the crucial difference is does this output has a structure or not. The structure is often a topology. Topology means we can have a distance between these guys. So we can say this one is more closer to 92 than 60. So consider structure of the output. Then if you wish to design a neural network, you should or any machine learning models. One of the first things you should do is consider the output, the structure of your output. Sometimes you also need to consider the structure of your input, but because the output, the structure output is related to the loss function. So it is most. I will argue that the structure of output is a little bit more important than the structure of input. Okay. So for the first case, if your output is discrete, that is just like a lottery case or MNIST, like 10 digits, although they are numbers, they are just symbols. So if your output is discrete, then you might kind of like make your output like just like what you do for classification, because you can actually give so for the MNIST there are 10 digits, each one corresponding to the probability of x equal to 0, which means the symbol, the output is x equal to 1 and x out is equal to 2. So by output these 10 things, usually you use softmax to make it more like a to make a logic become a probability. So you can literally get the PXI out of this neural network output. So you have a neural network right here and output something like this one. It's a softmax. And this input we will talk later. For any kind of input, then by using this neural network, they can output the whole probability distribution. So that is pretty straightforward. And you can use like cross entropy, or currently you can use the likelihood because you already got the distribution. Local likelihood, you can use the local likelihood, or maybe cross, pretty much the same as the cross entropy, or maybe like hair divergence if you wish. So That's pretty straightforward. So what about the regression output or the continuous output? It is the typical case is like if you have the if I send sensor to the has some values like the temperature from some sensor. If you get it for each second, you get x1 is the temperature of this sensor you has already get from maybe measure from a pipe or something. So this is temperature. So if you get the first three or first four one, and you want to predict the next one. So because the temperature is okay, if the actual temperature is like 33 degree and your prediction is like 32.8 degree, then also it's pretty accurate. It's not like the it is not like the discrete case. So of course you can still do so by so assuming that your temperature is between 0 to 100 degree. Then you separate it into split it into 100 ones. So for each integer degrees, you have one bin right here. So you can still output consider this, although it is a continuous real value. The temperature should be a real value. You can still split it into 100 different degrees and have certain precision. The precision is in 1 degree. That's okay. In many cases, if this precision is good enough. However, in this case, if you are using a cross entropy or other any kind of loss function, it would consider if your prediction is like 93, however the correct one is 92, you'll get a penalty, a loss, just like what your prediction is 60. So sometimes it will hurt the convergence of the model, and sometimes it will just work fine. So it is still something you can consider, but perhaps it is not the perfect one, or more the desired one. So another way to do that is simply forget about the probability distribution. You simply just like a regular regression model. You simply like given x1 to xi minus 1. Your output is like xi head. We just call it xi head. You can simply consider it as a regression, the normal regression model, just without probability structure. So you can still do something and using like a mean square error. You can still using a mean square error like to do so. Of course, you have a time series and you can generate the data you wish. Like every x1 to xi minus 1, you have I samples that you can use, and you can train your model. Your model have a weight like we just call theta. You can train this theta, find the perfect theta, the optimal theta that predict the value as close as possible to the ground truth. Then you can do that. Of course, you do that, and it should work just fine. And a lot of time, it's all you need. It's just that you don't have the error bar or error band that sometimes you might want to have, but it works. You can simply do that. So if you really need some probability structures, a common way to do that is we have an F to predict mu. So if we consider our output to be a normal distribution, it is a very often assumption that we output out. You can choose other predefined distribution, but if you have no preference, if you doesn't have a really good idea of what it is, you can simply use a normal distribution, and your f is actually output a mean, and you have another output. Maybe in the same network, because you have one neural network can have multiple output, or you can have a separate model. Usually we kind of just use the same one because they can share their weight. But you can do whatever you want, and output the standard deviation. Okay, it must be it is a positive real number. So your input is still the same, xi to x minus 1 and x1 to x minus 1. And your output is a normal distribution of mu I and sigma square I. So it is a normal distribution. So in this case, you can do, because you have this distribution already, so you can compute the log likelihood. So suppose the ground truth is xi. So then you can compute the log likelihood. I will go to the detail in the when we talk about the variational autoencoder. We'll talk more about the log likelihood. But because if you are using the log likelihood and because of the formulation of the normal distribution, it will kind of like a weighted mean square error. The weight is dependent on the standard deviation. So there's one concern about the output of this standard deviation or variation right here. Because we use a square right here. It has to be positive. It has to be positive. So if it is a neural network, it will output something. Can be positive. It could be positive or negative. So if we have to restrict the output to be positive, you can use any function you like to make it to be positive. So in the most common ways to do so is to use an exponential on the output as an activation, or use a soft path. This is more common to very often you can see people use this kind of function to make it to be positive. Of course, you can actually just use the absolute value or use the square. They might just work. But yeah, I don't see why. I kind of believe I haven't seen it very often. I've never seen that it actually used in some publishing models, but I don't see the reason that it does not work. Although it has some property that is not desired, because the direction, it is not a monotonic function. It is not like a absolute value or a square. It's not a monotonic function. Other than that, it should be works just fine. However, you can go to a more common way. I think subclass and exponential is pretty okay. So I don't see that make too much differences. But you have to make it to be a positive one, because the standard deviation and the square, the variation, the square of the standard deviation has to be positive. So let's talk about the input. There are many ways to do the input. If you are using MLP, multi-layer perceptual, then you can simply cut off the length of the input, because for MLP it need a fixed length of input. So you need to kind of cut off to enough, long enough length. And because the characteristic of MLP, so it will know what the position it is, like this x1, x2, x3 to xi minus 1. You may know that the position. Of course, it's relative to the I point, I minus something. Maybe we only go to I minus p, like the ARP models. So if you are using a RM model like LSTM or GRU model, so you don't need to worry about this thing, because we are going to talk about the recurrent neural network later, a little bit later, because it is going to be used. So we're going to talk it later, but the benefit of using recurrent neural network is that you don't really need to, in principle, you don't need to worry about the length. You can have a dynamic length of the input. Although in practice, when training, because you have to train it in batch, usually you still kind of need to design a length so that each input has a, in many situations, you wish each input to have the same length when training. So you have to do the padding or to kind of cut off the string, the sequence. But anyway, in a lot of situations, you only need to decide a length, like a P for like an MLP, long enough length. And so when you use a larger model, you always encounter the context window, like usually like a 8K, 16K, 32K, or maybe like a recent new model like I have 1 million context window. So it still has some window right there. So although in theory we are consider a length can be as long as possible, but in practice it usually just works just fine if you have an upper limit of the length, as long as the length is long enough. So in our homework next week, you will see the effect of contact length that affect for the text generation, to get a feeling about how much length will affect your output. Okay, then you can also use convolution, like which we are going to discuss later, as an example. That WaveNet is a typical example. A time series can be considered as a usually because we are doing the vision a lot, so we are usually consider convolution 2D. However, convolution 1D is the original convolution. The original convolution is convolution 1D. A time series is actually a perfect input for convolution 1D. So you still got a window, a kernel of a certain window. You can still do that, and it is perfect. So as long as your correlation is kind of locally, it is a perfect. It doesn't have to be strict locally, but if the local correlation is more important than longer correlation, it might be a convolution might be a very suitable architecture to model your neural network. So you can definitely use the convolution as your input. So convolution, just like MLP, you can cut off your input length to be a specific length, to have an upper limit of a specific upper limit of the length of the sequence. However, if your architecture is like an all convolutional neural network, it can have a dynamic length, just like LTM or GRUS. It's just that the last few layers have some limitations. Choice, you have used some like the full average. You have a spatial pool that average everything together. So you have a specific number of output. So you can either like choose a non-full convolution architecture, and just like MLP, you have a specific upper limit of length, or you can choose a full all convolution architecture and make it accept any length of input. So if you have no preference, if you have no preference so far, I would say that the first choice should be something like a length, upper bound of the length, length limitation. That would make things much easier to adjust. Make the architecture more easier to adjust. So transformer is also very popular to handle the sequence input. So transformer is actually use the key point of a transformer is using a attention layer. Because attention layer does not consider with the position. So usually, in a transformer, I'm trying to write a transformer, but the S, I'm writing S. Okay. Maybe I should plug in the power, so it's kind of slow. Okay, I'm trying to write a transformer, but it doesn't look like a word. So for a transformer, you usually give a positional encoder, POS. I'm trying to write a POS. So in addition to the original sequence x1, x2 to xn, it also embedding the like 1, 2, 3, 4, 5 in some way, like the position into the sequence, so that after the attention search or find out what the relation between the elements, it also can understand what is the position of each element that is exists in the origin. It got the information of the position of that element. So that is this is the way that how the transformer handle sequential sequential input, or the input that is a sequence. That is a sequence. So this is mostly because the different way of encoding the position. So there's usually some way to hack the larger range model to have a larger larger context window. Depends on the method of doing positional encoding. Also, we will talk about this more when we talk about large range model. But there are different choices of positional encoding. Okay, so that's pretty much about.
Let me go back here about how we implement this kind of formula into some concrete things that we can actually use. So if you have some simple example like what we will do, what we will give you in as a homework, basically you can just choose one novels or one books that you are you kind of like reading, or just a bunch of text, and consider each character as a element in this sequence. So you can try to, because we have only, if it is English, we have only 26 alphabet, and plus maybe you can just skip out the numbers or other bunch of characters. So you got maybe just the space and the English alphabet. You only have 27 things if you ignore the case. You can try to write a model that predict the next one using the previous one, which is just simply we are just describing the things right here is autoregressive models by using maybe MLP, and you can see that how the simple models, what is the capability of a simple like MLP, or I would suggest just using an MLP. But if you are willing to use the convolution, you can see the difference. But you can just simply using a MLP, maybe taking like the 20 or 30 characters, or maybe you can start with like 10 or 20 as the input length, and predict the next one, and you can see that how much text you would need to train something meaningful, and what is the relation between the data size and the length. So if you have a hard time to design the length, and you have already tried to do it, modeling it into MLP, and maybe you can try it with an RNN model like LCM or GRU, and to see what happens. Okay, so that's it for the basic implementations.